Okay, hello everyone. My name is Jada Lee. Today we're going to explore the exciting journey of reinforcement learning. So this is just not a history of algorithms. It is indeed a story of how we teach machines to move from simple imitation to complex reasoning and physical autonomy. A little bit background about me. So my career goal is to use AI and computing to solve the disease and equalize health for all. And reinforcement learning is a cornerstone of that mission. Feel free to connect with me through my LinkedIn account if you want to keep in touch after the presentation. So I hope we can have a wonderful time in the next 1 hour and a half. So what is reinforcement learning? At its core, reinforcement learning, or the RL as an abbreviation, is a type of machine learning where an agent, in this case, our friendly robot at the bottom, learns to make a decision to interacting with the environment on the top. So how it works, the agent will receive the current state and the rewards from the environment. And then based on that, the robot will choose an action. So that's the root of the interaction between the environment and the AI agent. After that, the environment then will respond with a new state and a new reward, which will be passed to the AI agent. This kind of cycle will continue over and over again with the trial and AI process. So the goal is simple but quite powerful. The agent learns to take actions that maximize the cumulative scalar rewards over the time through the trial and error. It's not giving the correct answers upfront. Instead, it explores and also make mistakes and improves, just like how humans and animals learn from the environment and then generate a sequence of the actions. So this kind of elegant feedback loop is the foundation of everything that we will cover today. From training robots to work to align the large language models with the human values. This kind of loop is the core part that we will cover in the next slides. Let's look at where the reinforcement learning is making the real-world impact today. Reinforcement learning powers autonomous drivings. If you can look at the recent huge development of the self-driving cars, where vehicles learn to navigate complex roads safely through the continuous interaction with the environment. It also drives the recommendation systems on platforms like Facebook and Amazon. It basically learns your preference to deliver highly personalized content. In robotics, reinforcement learning enables robots to master complex and motor skills, from walking to the dedicated manipulations through trial and error. In the healthcare and the life science areas, reinforcement learning is also being used to optimize the treatment plan and also discover new drugs and even control the medical robots with precision. In the finance and trading areas, and the reinforcement learning algorithm also learn how to optimize the trading strategies by maximizing the long-term returns while also to manage the risk. So this kind of different types of the practical examples show how reinforcement learning has moved far beyond games. It's now a core technology solving the real-world challenges across the different disciplines in the industrial area. For today's talk, we wouldn't focus heavily on the application and the implementation of the reinforcement learning. Instead, we will dive into the most popular layer of the reinforcement learning, which is the core algorithms and the optimizations. So let me give you a quick review of the today's content that I will cover. We will firstly start with the tracing of the evolution of the reinforcement learning, and from its earlier foundations to all the way to its modern applications in the large language model alignment and the robotics. We will also begin with the foundations, which is imitation, learning, and behavior cloning. Then we will move to the policy gradient era and also the classical reinforced algorithm. Next, we will cover the actor-critical architecture that brought much needed stability. We will see the deep reinforced learning breakthrough with the DQN that combined reinforced learning with the deep neural networks. Then we will also cover the PPO, the workhorse algorithm behind today's large language models, which was developed in 2017, followed by the human alignment techniques from the reward learning to the reinforced learning human feedback, and then the more efficient DPO algorithm. We will also cover the new frontier of the reasoning and the chain sort of optimizations, then move to the robotics and the physical autonomies using the model-based reinforced learning. And finally, we will look at the meta reinforced learning and the generalization, the path toward more adaptable and also more AGI-like agents. So this presentation basically follows the journey from the simple imitation to the trial and error optimization to deep learning integration and human alignment. And finally, it will end up with the reasoning, physical embodiment, and also toward a more general super intelligence. So let's get started with this very beginning, reinforced learning, evolution, and foundations, which we will cover in the next slide. So for a long time, reinforced learning was synonymous with mastering games like AlphaGo or chess. But today, the narrative has shifted. Reinforced learning is no longer just a gaming sandbox. It has become the fundamental engine behind the human-aligned AI and autonomous physical systems. We were moving from the control, which is managing a robot arm on a factory floor, to reasoning, which is to enable an AI to think through the multi-step problem. So that's the evolution of the reinforced learning. Fundamentally, I'd like to start with the imitation learning or behavior cloning. Think of an agent as a student watching a master. The goal is simple: minimize the difference between the agent action and the expert's actions. Mathematically, we will maximize the likelihood of the expert actions using the function formulated at the right bottom. So this is a function to maximize the expert actions using the function formulated. This math function is to maximize the likelihood of the expert action given that state. Basically, we can adjust the parameter theta to maximize the probability that the agent picks exactly what the expert picked in the specific state. So it is to achieve the perfect fitness between the agent action and the expert actions. However, we hit a wall if the agent deviated from the expert path. It didn't know how to recover, right? So which leads to the compounding errors. This legacy still lives on today's in the supervised fine-tuning or SFT phase of the large language model. In 1992, the reinforced algorithm changed the game. Instead of copying, we directly optimize the policy, which is p theta, to maximize the exported reward. The math shifted to the reinforced rule equation of the red highlighted math area. So this reinforced rule equation moves from copying to optimizing by directly adjusting the policy to maximize the reward signal. If you look at the formula at the bottom of this kind of functions, you can see that if the reward R at the end of this equation gets higher, and then we push the policy gradients to make the action more likely. If the reward R gets lower, or negative, we make the action less likely. That is the probability of that action. So this allows for continuous action space and the model-free learnings. The major flaw, however, was the high variance for this kind of reinforced rule equations. One lucky or unlucky trial could swing the weight too far, making the learning process is incredibly unstable for using the reinforced algorithm. Sutton and his colleagues introduced a more stable architecture, the actor and critical architecture in 1999. The actor decides the action, while the critical estimates how good the current state it is. So it is like value functions. By using the advantage function, measuring how much better an action was than the average in the bottom mass function AST, AT equals to the QST AT minus the VST. The critical smooths out the noise. This architecture actually remains the backbone of almost all modern deep reinforced learnings, including the reinforced learning human feedback used for the GPT model series. So this kind of advantage function, which was listed in the bottom, is to solve the high variance problem of the reinforced rule, which I introduced in our last slide. We split this logic into two parts. One is the actor, which we call it the policy, and the second part is a critical, which we call it as a value estimator. You can see that instead of using the native reward variables of a reinforced rule, and then the equation from the last slide, right? This actor-critical equation is to tell the agent how much better was this specific action compared to what we usually expect from this kind of state. So this is a really stabilized training process of the learning algorithm. In 2013, the reinforcement learning had its breakthrough moment when it met the deep learning through the DeepQ network, or DQN we call it as an abbreviation, introduced by Minhan and the colleagues. The key innovation was using a neural network to approximate the Q function, essentially predicting the expected future reward for each state action pair. And to make this kind of work in a complex and high-dimensional environment, like the Atlas games, they introduced two secret ingredients. One ingredient is experience replay, a memory bank that allows the agent to learn from the past experience and break some harmful data correlations. The second secret ingredient is the target network, so which provide a stable training target and prevent the wide oscillations that progged earlier attempts. So this is the two parts of the DeepQ network that are used to power the reinforcement learning. One part is experience replay, and the second part is the target network to estimate the loss. Later, the double DeepQN network fixed the notorious overestimation bias, where the agent becomes overly optimistic about the poor actions. Looking at the equation here, the DQN loss function, if you look at the on the bottom left, combines the classical Bellman equation bottom right, which was described in the bottom right areas, with the deep neural network. It trains the network to make its prediction match the target values, which was shown in the first part of the loss functions. And to match the target value of the best possible next actions, which is to enable the reinforcement learning to scale to the real-world vision environment for the first time. So that's kind of what the deep learning neural network helps reinforce learning. Next, we will come to one of the most important algorithms in the modern reinforcement learning AI, Proximal Policy Optimization. We call it PPO, introduced by John and his colleagues in 2017. So the problem with earlier policy gradients method with the traditional update often took steps that were too large, which could completely destroy a previous good policy, a phenomenon which is widely known as catastrophic forgetting. So the PPO network basically solve this kind of brilliant idea called the clip objective. As you can see in this kind of equations in the bottom, instead of blindly applying a large update, the PPO, Proximal Policy Optimization, clips the probability ratio between the new and also the old policies, right? And this ensures the new policy does not deviate too far from the old ones in the single step. So if our promising update suggests making an action 10 times better, PPO will gently clip that enthusiasm or magnitude, for example, limiting the change to somehow safer like 1.2 times, providing the stability needed for the large-scale trainings. So that's the core part of the PPO using the clipped objective to minimize the unstability. So this is why the PPO becomes the golden standard for the alignment of a large language model like ChatGPT through the reinforcement learning human feedback, RLHF. It basically brought the reliability and scalability and stability that previous method does not have. Here is another fascinating turning point in the reinforcement learning history. What if we cannot write a math formula and equation for the reward? For example, how do you define a good poem? How do you define a good writings from the poetry? A helpless answer or safe action? You cannot easily score this with numbers, right? So in 2017, Paul Christina, and also with his colleagues proposed a powerful solution, learning the reward directly from the human reference. So this process is elegant, is to show how a human two different agent behaviors or outputs. Ask like which one is better, then train a reward model, which is the reward model which is allocated as the R theta to predict and mimic human judgment. So this kind of proposal perfectly to solve the problem that if we cannot write a mathematical equation for the reward. This simple idea transformed the reinforcement learning from just maximizing the game scores into a powerful tool for the human alignment. Looking at the equation at the bottom of the slide, the Bernoulli-Terry model, it actually calculated the probability that one response is preferred to over another. The model used the exponential of the reward scores so that even small difference in quality create a clear preference, while the denominator normalize everything into a clean probability between the 0 and 1 using the exponential functions. By training on thousands of human comparisons, we adjust the reward model's parameters to better reflect human values. So this shifted the AI and move AI from pure optimization to the true value alignment. After the PPO became the standard for the reinforcement learning human feedback, researchers ran into a new challenge. PPO is computationally expensive and quite faker when applied to the large language models. In 2023, a breakthrough called Direct Preference Optimization, or DPO, changed the game. The key side of the DPO is elegant. The language model itself can act as a open reward model. So that's the game changer. Instead of training a separate reward model and running a complex, unstable PPO loop, DPO use a clever mathematical shortcut to optimize the policy directly from the human preference. If you can remember in our last slide, we introduced how the human reference has been introduced to use the value-based exponential functions, right? So this is the last slide, how we turn the reinforcement learning into a tool for the human alignment using the this kind of reward model. But here, for the DPOs for this slide, instead of training a separate reward model and running a complex unstable PPO loop, DPO used clever equations to optimize the policy from the human preference data, as shown in the DPO object function in the bottom end of the slide. It elegantly increases the likelihood of the preferred response while decreasing the likelihood of the rejected ones, all in one clean training loop. The result is much faster, more stable training. Today, the DPO is considered as the gold standard for turning the base models into a helpful chat-like assistant, especially in the open source communities, because of the DPO objective function. We're now entering the exciting new frontier of the reinforcement learning for this slide, which is called reasoning and the chain of thought. So traditionally, large language models were trained to simply predict the next word. But for today, we use reinforcement learning to teach models how to think in a step-by-step. The core idea is to reward the model not just for getting the final answer in a direct way, but for the quality of its logical intermediate steps. So this approach bridges the gap between the system 1 thinking fast intuitive response and the system 2 the slow, deliberate, and step-by-step reasonings. So the key technique include the chain of thought optimizations, which is called COT optimization, and where the models is to reward it when its reasoning step is to the correct answer. And also we provide the second part of this core technique is the verifier, where one reinforcement learning agent checks the logical consistency of another. So this core technique consists of two parts. One part is the COT optimization, another one is the verifier, is to using the reinforcement learning agent to check the logic of the another agent. The goal is quite ambitious. It's to move the AI from simply generating the fluent text to generally solving complex problems like thoughtful reasoners. This kind of transformation is very beneficial for the agent-based coding or the mathematical problem solving. So this direction we can see in some models like the OpenAI's O1 series or represent one of the most promising paths towards more compatible and also more agentic AI systems. Moving from the languages to the physical models brings us to the model-based reinforcement learning and robotics. So this core concept is to learn a world model for the AI agent, essentially a mental simulation of how the physical world will work. Instead of blindly trying actions into the real world, the agent learns to predict what will happen next. As shown here, given the current state and the action of that neural network, the dynamic models will predict the next state state and reverse. This allows the agent to imagine thousands of scenarios internally and practice without risking expensive hardware. So this approach delivers huge sample efficiency. You don't want like $1 million to a robot to. You don't want a $1 million robot to crash 1,000 times to learn to work, right? And one of the another most important technique used in this model-based reinforcement learning for robot is the simulation to real, sim to real domain optimization, randomization. So which is to deliberately to make the simulators messy and inconsistent. The robot experience was and are heavier, lighter, and sleeper or noisier than realities. That's the truth of the robot environment. And but after learning a policy that works across a wide distribution of the environment, the robot becomes robust enough to handle the unpredictable real world. Mathematically, in the bottom of these equations, we optimize the policy theta to maximize the expected reward J across many possible environments. So which means the scaling of the environment is also very important for the model-based reinforcement learning in robotic areas, not just one perfect simulator. This combination of the world's model with the simulation to real is the key to bring the capable, safe, and reliable robots into our home and hospitals in the future. Finally, we reach one of the most exciting frontiers in the reinforcement learning, and which is the meta RL and the generalization. And we call it learning to learn. This kind of a concept. So although the standard reinforcement learning trains an agent to master one specific tasks, right? And the meta RL trains an agent to quickly adapt to the entire new tasks for work. The meta policy, often called reinforcement learning square, learns from a wide distribution of the previous steps during a slow training phase, so that when it faces a brand new task, it can still adapt in just a few steps. So that's the core part of the meta policy, which is called RL square. Unlike the standard reinforcement learning, which optimizes for single environment, the meta reinforcement learning agent maximizes the expected reward across a whole distribution of the tasks. So, for example, if you look at the bottom right of the meta objective equations, a powerful technique that supports this kind of hidden side experience replay HER is that let's just imagine a robot is trying to hit a target but missing 1,000 times, right? Missing 1,000 times. And in normal reinforcement learning, it would learn almost nothing because it only gets a reward for a perfect hit. But for the HER, which is the hidden side experience replay, HER solves this by storing this kind of fair trajectory and relabeling them and allows the robot to learn valuable lessons even from his behaviors. So this is a very important theory to self-training and self-improving the agent by the failures and also the trajectory of the experience. So this combination enables the robots to generalize across many different environment and tasks. That's the reason I mentioned that this kind of meta-RL is more generalizable to different environment. And meta-RL represent a critical step towards the AGI, creating agents that don't just solve one narrow problem. It's about building a system and that can evolve with their own curriculum and continuously get better and better. So this is where the future of both intelligent robot and truly capable AI system is heading to. To wrap up today's lecture, let's look back at the remarkable journey of the reinforced learning. As shown in this table, reinforced learning has evolved through several distinct areas, right? Starting with imitation learning, simply copying the expertise, moving to the policy gradient method, focused on the trial and error reward optimization, and then the DQN breakthrough that brought the deep learning integrated into the reinforced learning algorithms. And then it goes to the PPO, which delivered the stability needed for the large language model systems. And then after that, the reinforced learning, human feedback, and also the direct preference optimization, DPO, which enable true human alignment. And finally, the model-based approach and the meta reinforced learning, which opens door to the physical autonomy and also the environment generalizations. In essence, we have progressed from the tubular Q learning, tabular. We actually moved, the reinforced learning has actually moved from the tabular Q learning, which is for the small games, and to the deep reinforced learning, concurrent like the Terra game, to the PPO and the DPO, powering today's human preference alignment in the large language models. And now most cutting edge research is toward the model-based and also the meta RL systems, which is capable of real-world reasoning and adaptation in the physical autonomies. So this kind of a unified goal is really clear, developing the intelligent agent that can plan, reason, and act safely in a complex and open-minded and scaled environments, whether not only in the healthcare, finance, robotics, but also it is beyond so many industrial area applications. So this kind of evolution of the RL reflects not just better algorithms, but a fundamental shift from the AI that truly understand and also aligns with the human values and intention. Yeah, so let's a review of the journey based on that table. So here comes the key takeaways that I want to provide you for today's lecture. Looking back, the last 30 years have witnessed the reinforced learning evolve from a rich control theory into a unified framework for behavior optimization across many domains, right? And now, as we look at forward, let's look forward. In the next 30 years, the future is even more exciting than what I can foresee. We will see that the large language model shift from the simple chatting to the reasoning and agentic behaviors. So that means the system can think, plan, and act autonomous. In robotics areas in the next 30 years, we will move from the controlled factory force into our unstructured homes and everyday environment, where the robots must understand human intention, human emotion, and also understand the human values in dynamic and real-world settings. At the heart of this kind of entire journey is the one central theme that I want to provide you is that the alignment between the human intent and the machine executions to ensure that this kind of central theme for the alignment between the human intention and the machine execution is to ensure that the AI system not only perform well, but also do what we truly want them to do in a safe and beneficial way. So this kind of alignment really define the success of AI in the coming decades. All right, so I think that's all for today's video, and I'm really happy to take any questions you might have. And for those who would like to connect, you can find me on the LinkedIn link on the screen at the bottom. Feel free to reach out. I'd love to continue the conversation. Thank you again for your attention and time. Bye bye.